Hi, thanks for joining us today. We're going to be talking about lesson 7-5, the derivatives of a logarithmic functions, blah. We can find the derivative of a natural log function by using the formula for the derivatives of inverse functions. This was in lesson 7.3. If you want to refresh that lesson right now, that'd be a good idea. But the basic idea, and you can see this on page 141, is that if I have f and g and their inverses, the derivative of g is 1 over the derivative of f with g as the inside, g as the input. So, if y equals e to the x and y equals natural log are inverses, let's just call f e and call g natural log. We already know the derivative of e to the x is e to the x. That's what makes it the most beautiful function in the world. So the derivative of its inverse function, which we would call g prime, because g prime is ln, right? That's this part. Using the formula is how we get this part. Okay, that's why they got this. F prime of g. F prime of g. So they're just replacing x. They're replacing all the x's with natural log x. So they replace all the x's on this side with natural log x. And that's how they get this. And then using the stuff we talked about, e to the natural log cancels out. We're just left with x. Alright, so here we go. Using this rule, we can do all the other functions we want. So this is the most basic version of it, what we just proved, more or less. You don't have to memorize that proof, but you have to be able to do these 4 rules. Applying it to another log, you would have the same exact proof with one little thing, and it comes from the change of base formula, which we'll show at the end. But just to be clear, with a practical example, the derivative of log base 2 of x would be, can you do it? Can you apply this rule really quick on a simple one? 3, 2, 1. 1 over x natural log 2. Just that weirdness attached. That's it. The more important formulas are the chain rule forms. If you just memorize this, you don't have to memorize these. If you know this, you can do those. We have keep the inside the same, multiply by the hook on. U prime is still a hook on here. A more useful form, especially for integration in the next unit, is u prime over u. So we keep the inside, we put the inside, u. This is whenever the inside of the log is more complex. Just put that inside right in the bottom. And the top is the derivative of the inside. A log. Same thing here, u prime over u with that log, with that extra bit, because that's its formula. Now, these are both chain rule forms. Let's write down the chain rule. I told you before, we're going to use every opportunity to write this down again. Can you write it down by heart? Do you know the chain rule, the general version of the chain rule? I'm talking about, do you know what the derivative of this guy is yet? By heart? By heart? 3, 2, 1. We take the derivative of the outside, we keep the inside the same, and then we multiply by the derivative of the inside. Derivative of the outside. The derivative of natural log is 1 over whatever was inside of it times the derivative of the inside. Just a chain rule. You've been using it all year. You used it with exponentials in 7-2. Now we're going to use it for derivatives. Try these out. You should be able to do them regardless of what your grade is in this class. You are a good calculus student if you've made it this far. So try them out. Here we go. 3, 2, 1. Did you remember to take the derivative of both sides and label it? So we divide by the original inside, which was 5x. And then what's the derivative of 5x? It's just 5. Done. If you simplified that, you would get something interesting. You would just get 1 over x. So if anyone did all these right, you should think about why. I'll return to this at the end of the slide. Why are these the same? Why is this guy the same as the derivative of just natural log x? All right. If you didn't get this one right, but now you understand what I'm talking about, where we have the inside matchy-matchy, and the top is just the derivative of the inside, try that out here. 3, 2, 1, label, label, label. The inside was 3t squared minus t. And what's the derivative of 3t squared minus t? Because that's what we're going to put on top. 6t minus 1. Done. Differentiation should feel really good at this point. It's your old friend, not like integration. The mean new kid at school. Did you figure out this yet? All right, over here. How are we going to do this? Careful, careful. If you said or thought product rule, you're right. Product rule. This is a multiplication of two functions. Whenever I see two functions without a symbol between them, that's a product. So h prime of x, first times the derivative of the second. What's the derivative of natural log of x? Did you memorize it? It would be pretty cool if you memorize it instantly. It's 1 over x plus the second guy times the derivative of the first guy, which is just 1. And again, this is a perfectly acceptable final answer. But if you want to simplify it, you would get something kind of interesting. You would get 1 plus natural log x. It's only kind of interesting. Don't worry about it too much. All right. Just to return to this example really quick. I hope you all three make sense. If you're having trouble understanding what I did, try while you're watching it. Try asking me. Come talk to me about it. I'm happy to have a discussion. We have a method 2 on problem number 1. Y equals natural log 5x. We can use log rules to call that natural log 5 plus natural log x. Because with multiplication inside can turn into addition. So then taking the derivative of y, natural log 5 is just a constant. It is just some number. And then the derivative of natural log x, what is it? 3, 2, 1, 1 over x. So both of these have to agree. That's why it would cancel. Again, I would never do it that way. I would never in a million years do it. Calculus is easier than pre-calculus because these rules matter less. Not infinitely less. They do not matter. They matter, but it's much easier to just take the derivative at this point. Derivative of 5x needs to be second nature. All right, a weirder example. This is a non-calculator. No calculator. Don't use your calculator. I want you to try it out. This is a weird transformation. This is a throwback transformation. You could go all the way back to section 1-2. I handed out a blue sheet of paper at the beginning of the year. I think it was blue. That had all the transformations on it. You could use that, but no calculator. 3, Do all of them. Do all the thing. Do the whole problem. Try it out. What's going to hurt? 3, 2, 1. Here we go. So the rules for graphing when we have an absolute value around the inside, this is the whole reason we do this transformation. You have whatever the parent graph was, which for us, our natural log guy has a vertical asymptote at the y-axis. It blows up like this. Whoa, that's way too fast, actually. Natural log is one of the slower people. Like that. Definitely increases always. Definitely concave down. Okay? So the rules for absolute value on the inside say delete everything left of the y-axis. Delete everything above the negative x-axis. Done. Because there was nothing there. Then reflect everything over the y-axis. So we basically copy this graph, a mirror image of it in reverse. So we have that point, and we have the negative version, like that. Also concave down, but this guy is forever decreasing. Now, if you didn't get that right, retry part B. I'll give you some time, although you could have infinite time if you wanted by pausing the video. 3, 2, 1. All right. So for the right half of the graph, the absolute value didn't do anything. It's the original graph. So if x is positive, the right half, the derivative should still be the same as natural log. Okay? Nothing changed. What about when x is negative? If the slope here was like this, what's this slope over here? So if that slope was like, did you pause the video? Did you try it out? If that slope, when x equals 1, was 1 over 1, this slope over here, you might have said was 1 over negative 1, or perhaps just a negative 1 slope. That these are actually opposite reciprocal slopes. So the trick here is that it's not negative 1 over x. It's not that. Don't say that. It's just still 1 over x. Okay? So, absolute value does nothing when differentiating. Only when differentiating natural log absolute value, the absolute value can be ignored. Okay? The absolute value is really important here. It lets us have a function that has the domain everywhere besides 0. So this function has domain everywhere, and its derivative is the same as natural log. This is really important for 7-6. If you didn't quite get this, we're just going to be using this fact in the next lesson. So don't worry too much, but it'll make sense in 7-6. Okay? We're using this to get a function with a bigger domain that has the same exact derivative. Okay? It's not negative. So to do this one, we're going to ignore the absolute value. Try this out. Ignore the absolute value. 3, 2, 1. Inside the same. On the bottom, derivative of this with respect to y on top. 3, 2, 1. Done. Next. So we can simplify logarithm functions before differentiating them. In this case, by simplify logarithm functions, we mean expand. And the reason we want to expand here is that if you wanted to do this derivative, keeping the bottom the same is easy. Or sorry, Keeping this the same, that's the easy part. Taking the derivative of this would be hard. Why? Give me a reason. Think about a reason. Why is taking the derivative of this guy so hard? 3, 2, 1. Well, it's a division. We see some division. So we'd have to use the quotient rule. We need the quotient rule. We would need the product rule. Scary. Where do we need the product rule? Right here. That's a product. It's a product a lot of people neglect. Plus needing product rule. We would never differentiate that. There's so many errors. So we expand first, if you can. So use logarithm rules to expand this out. Try it. Please, please, please try it. So, did you try it? Did you have something nicely written? We didn't differentiate it yet. You better not say dy. You have something expanded. So the first thing I want to take care of is the division. So I'll keep the top the same, 2x. Minus, because dividing inside a log can change to minus outside a log. And then multiplying inside a log can be changed into adding outside a log. Anything else you can simplify? 3, 2, 1. I hope you noticed that this is a power. So we can bring that power out. And that would be much easier. Like we are saving us light years of time. There will be test questions that are designed to see if you know to do that. Because this is saving students tons of time. Trust me. This power is stuck inside. Don't take that power out. That's not okay. It's plus 1. Don't break this up into natural log x squared plus natural log 1. Addition inside a natural log cannot be broken out. You are stuck with it. And don't start recondensing it either. This is nice simplified. So again, we expand first. I'll write it down. And then differentiate. So now is the first time we're going to take the derivative of anything. So now is the first time we write out dy dx. Derivative of natural log. 3, 2, 1. Do you know it yet? Did you memorize it yet? 1 over x. Keep the constant. Differentiate this guy. Original inside on the bottom. Derivative of 2x plus 1 on top. That's nice. That would cancel. Minus. Keep that there. Parentheses. 2x on top. Were you able to get that? If not, I would try it again right now. Cover this up. Make sure you can get this derivative again. This should not be hard. It should be easy. 3, 2, 1. All right. Use the change of base formula to prove that rule. What's the change of base formula? Do you know it without looking at your notes? You need to. The change of base formula says that log base A of x is the same as natural log of x, the input goes on top, divide by natural log of A. All right, so the derivative of the left-hand side, what we're trying to figure out, would be the same as the derivative of the right-hand side. Hopefully something easier, right? That would be the idea. I know a lot of students think we need the quotient rule. It's not the quotient rule here. Why? You should be able to think of the reason. We've been doing it for months. Since natural log A is constant. So that's equal to 1 over natural log A. We can leave constants alone when we're differentiating. Times the derivative of natural log x. And what's the derivative of natural log x? Well, do you know it yet? We've done it so many times in this video alone. 1 over x. And we can write it as x, ln a. So that's the proof. Okay? You don't have to be memorizing this proof. But if you got stuck on a test with a log base A question, use the change of base formula. That's why you'll memorize it. It's a break in case of emergency type of thing. 3, 2, 1. Last. All right. Try this out yourself. You should be able to do this. Take the 3, 2, 1. Did you write something down? If nothing's on your paper, you're not trying. I'll give you another chance. 3, 2, 1. You need to take the derivative first. If you plugged in 2 first, you are very far behind in terms of your calculus knowledge. Plugging in 2 first is the exactly wrong thing to do. Derivative first. Y prime equals. Sorry. So we're going to use the change of base formula. You could use the change of base formula, or you could just do the rule. Same. Natural log 2 on the rule, and then 2x. I kept the inside the same. The derivative of the inside, natural log of the base. If you used the change of base formula to do this, that's fine. You should have gotten the same thing though. You should have gotten the exact same thing as me. So if you haven't done it, try that out. So y prime of 2 is 2 times 2, or 2 squared plus 1, natural log 2. A lot of crazy 2's there. 4 over 5 natural log 2 would be a simplified answer, but again, this is okay. Thank you so much for watching. You should be able to do the whole homework assignment. I know this was a longer video. Thanks for staying tuned. Thanks for watching the whole thing. Good luck on the homework. Ask me if you have any questions. Have a great night. Have a great day.